Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Hi, I'm Daniela Tropea, and I'm Associate Professor of Molecular Psychiatry in Trinity College Dublin. Today I'll tell you the story of how basic research led to the discovery of new treatments for brain disorders, and how improving the symptoms of a rare condition pointed the way to help many more. And this is only the beginning. Along the way, we keep learning, aiming to design smarter studies and to find solutions tailored for each group of patients.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius podcast. My guest today is Daniela Tropea. We're going to talk about turning basic brain science into treatments to help people. Daniela is an associate professor in molecular psychiatry at Trinity College Dublin, Ireland. So welcome, Daniela. Thanks for coming.
Thank you, Richard. It's a pleasure. Thank you for inviting me to be part of this podcast.
Oh, no problem. Yeah, tell me a bit about your research and how you got into it.
Great. So I have a very strong background in molecular biology and neuroscience, which I did in Italy. And then once I saw, and during my PhD, I was studying the brain, the development of the brain and the brain changes and function. And I really wanted to work in this field. So one day I saw a seminar of Professor Sur in Trieste. Professor Sur works at MIT, and I said, "Oh wow, I really would like to work with this professor." So when I finished my PhD, I actually asked him to join his group, and he said yes. So I moved to Boston, MIT. So my wish was granted. So that's where my story starts. The story is that I was studying the molecular mechanism, the genes that control the development of the brain, and to do so, I should do an analysis of a long list of genes. It was a standard analysis of the time called the microarray analysis. And there is a standard way, which is to look at all the genes and rank them by several parameters. But I was also lucky that at the time there was another group at MIT who had generated a new software to analyze gene set. And so I could try this software on my genes and the gene list. And so I could analyze this, the outcome of my research in two different ways, the standard way and the new way of gene set analysis. And so it was really interesting because I saw that a lot of the genes and the mechanisms that were controlling brain development had nothing to do with the brain. They had to do with growth, with metabolism, with immunology. At the time, this was quite new. And so I was surprised, but at the same time, this was sort of epiphany for me to see that how the systems are connected. And so I had to select some genes to validate the system, because it's very important in science to, once you have a finding, to validate with multiple experiments. And to select the genes of interest, I also used my past experience on the study I did in Italy. And in Italy, I studied a lot growth factors in brain development. So there was a particular factor which attracted my attention because it came through both the standard method of analysis and the new gene set analysis, and also because it was very resembling of one of the growth factors I was studying during my PhD. So these factors that I decided to follow was the insulin-like growth factor 1, or IGF-1. This is a factor which is known to be involved in growth and in metabolism. But
VEGF, the vascular endothelial one, was that present as well?
Was present as well.
Okay.
Yeah. However, the other reason is because, as I said, I found extraordinary similarities between IGF-1 and brain-derived neurotrophic factor, BDNF. BDNF is a factor which was well known to be involved in brain development and function, and it had also therapeutic potential. So when I had to decide which one to choose, I chose the IGF-1, and I actually did the experiment, a physiology experiment, in which it was proven that IGF had the power of control the rearrangement of connections in the brain. And so we have this first publication, and in which we proved this. And at the same time, though, there were some discussions going on between the team of Professor Sur and Professor Rudolf Janisch, who still is a professor in the Whitehead Institute, our neighbor. And he had generated a model to study a rare neuropsychiatric condition called Rett Syndrome. And this is a very severe syndrome associated to mutation in one single gene, MECP2, which is expressed everywhere, but it's particularly important for the development of the brain. And patients with this syndrome are very severely affected. They have a variety of symptoms. They appear normally for the first 2 years of life, and then they show regression of acquired skills. They show an ability to move their hands purposefully. They have stereotypies. They cannot talk. They cannot walk. They have respiratory problems. They have seizures, anxiety. I mean, a variety of symptoms, and they're not always present, but they could be present with a variable severity. So each patient is different from one another, but they're all very severely affected. Anyway, Professor Janisch had found that BDNF was actually able to rescue the symptoms of Rett using his model. And he was talking to us because he wanted to understand a little bit better the mechanism of action of these growth factors. So at that point, I actually made a connect, which is, okay, IGF-1 has activates similar mechanism activated by BDNF, and it also controls remodeling of brain connect. So why don't we try IGF in the rescue of the phenotype? So I got in touch with a PhD student in Professor Janisch's lab, Emanuela Giacometti, also Italian. And we decided to try. And we tried giving the models both the full-length IGF, but also a little portion of IGF, the functional peptide, which also worked. And I did my experiment, and both molecules worked. We also focused on the active peptide to measure all sorts of parameters, like the activity of the cells, the strength of connections, the number of connections. And there was never a rescue, but there was always a significant improvement. So this preclinical, evidence showed that IGF and its active peptide could indeed improve the symptoms of Rett syndrome. And this was of interest, of course, of the community of Rett patients, but also clinicians.
Oh, how did you administer the IGF-1 and or the peptide? How did you give it to patients? Did you do a clinical trial where you actually gave them more of these compounds, and what happened?
In the preclinical model, it could be administered by either IP injection, intraperitoneal, or subcutaneous injection. In the clinical trials, the IGF was administered like insulin, so pinch subcutaneously.
Okay.
Yes, so basically the big interest was that IGF had already been used in pediatric clinical trials, because it was used to cure dwarfism. So there was the protocol already approved, and it was safe, at least in these patients. Nonetheless, it needed to be tested on the patients with Rett syndrome because these are very fragile patients. So the first tests were safety tests, and there were two studies going on simultaneously. One a clinical study in Italy and one a clinical trial phase 1 in Boston at Children's Hospital. And I've been lucky to be involved in both of them at different times. But both studies showed that it was safe to administer IGF-1, and there were also some advantages, some improvement in some of the patients. So this prompted to the starting of phase 2 clinical trials for IGF-1, and it was run in Children's Hospital, and there was some improvement observed in terms of social abilities and decrease in stereotypies. But unfortunately, these were not two parameters that were indicated as working for the Rett syndrome trial. So the trial for Rett syndrome was discontinued. However, IGF was then used in other trials on disorders of the autism spectrum, because it's very, those are symptoms that are very heavy in patients with autism. So at this point, we can think, okay, so this is the end of IGF-1 and Rett syndrome. Well, sort of. However, you may remember that when we tested the IGF, we also tested actually the active peptide of IGF. So when the preclinical study came out, some companies who were working on the peptide started running the clinical trials for the peptide for the pediatric use, and they developed additional compounds which actually worked much better than IGF-1. So they were administered either subcutaneously or actually in an oral preparation. So their preparation was oral, and they passed all the phases of clinical trial until one of them, actually, DEBUT, was approved in 2023 as the first treatment for Rett syndrome, approved by the FDA. So I'd like to stress that this treatment does not rescue, it's not a cure, but there was an improvement in many symptoms. And in fact, additional trials followed to check if it was actually also safe to administer for a longer time this compound, and it was. So this is a story where basically, it started all with basic research, and then basic research was turned into applied research, and then eventually we find treatments which potentially are good not only for Rett syndrome, which has been already approved, but these compounds have now been tested in clinical trials for other syndrome, Phelan-McDermid, Fragile X, and there is evidence that they can actually work also for autism and Parkinson's disease. So potentially these compounds have a larger impact. So I learned 3 main lessons. Yes.
Why do you think it's affecting the Rett syndrome, and why would it have these other possible effects? What's the reasoning?
So first of all, there are evidence that, some clinical trials already showed that there is a positive effect. What I think is the reason is that IGF is a molecule that it's kind of a homeostatic controller of the body and the brain, and it works. In fact, it provides an effect only in, let's say, in the models with the disease. The treatment of controls did not produce any significant effect. So it's like an homeostatic, like it adjusts a little bit what's wrong. But in particular, Rett syndrome is a great model for studying a lot of other disorders, because the gene that's associated with Rett syndrome, MCP2, is actually controlling a lot of mechanisms. It actually controls the expression of genes, and so indirectly controls a lot of other mechanisms involved in other disorders. So in fact, this particular part of the study, which lasted for more than a decade, taught me 3 main things. The first is that we should value basic research, because it all started with basic research. Second, that studying a rare disease is also useful because it may actually lead to broader applications, and some rare diseases are much better characterized, at least genetically, so it's easier to create models and understand what's going on. But the third lesson I learned in all this process, where I work with scientists, clinicians, and also pharma companies, is that the patients are not all the same. The patients are very different in their basic presentation, but also in their response. And this was clear in the trials, but I myself, I had seen some of the patients and some of the data, and I could see that some of them had huge benefit, while others had no benefits at all. This could be a problem for rare disorders because this huge variability in the response and the rarity of the condition can really hamper the significance of the result. And in fact, there are other trials. In particular, I know one trial of a drug that improved the respiratory phenotype. And I talked to a lot of parents, and they were in the trials, and they say, "Oh, I'm sure that my child is getting the drug and not the placebo because they improved so much. I could see they having the respirator, and now they can breathe without a respirator, and this makes them eat easier, being happy, and so." But unfortunately, because of this variability of the response, the trial was, even phase 3 was not continued, and the drug was never approved. So what I'm trying to say is that this drug would have actually been good for a subset of patients, and there are not the tools to actually identify this subset of patients. And so when I moved to Trinity College in 2009, I actually had two focus in mind for my research. One was to understand the mechanism of action of IGF and the related compounds, how they work. Are they the same? Do they have common or different pathways? Are they good for all patients? And the second goal was identify some markers for not only identifying different cohorts of patients, but also to measure the efficacy of the drug in an objective and quantifiable way. And so my team and also other teams actually showed that measuring brain activity could be a good hint. Brain activity is correlated with the severity of the phenotype, and they could they could identify different subgroup of patients, and they could identify, for example, the patients that respond to epileptic drug and those who don't. So there's active research in the field to push for this analysis and possibly generate biomarkers, so specific protocols that would distinguish different groups of patients. But I also have hints that actually even in the blood there may be something that could be correlated with the severity. I saw this in the trial with IGF-1 where we actually correlated the severity of the breathing phenotype with the expression levels of RNAs, which are particular kind of molecules in the blood. And there was a difference which was correlated with the severity of the phenotype. So these studies would require much work. However, I'm faithful that they could lead to a good outcome. So we have to identify what are the conditions and what are the molecules that could tell us, reveal the biomarker. And so I'm continuing this research, and I also got the chance through this research to interact with the people, the families in several nations, US, Ireland, and Italy. And they are, to me, they're very inspiring. Sometimes when research gets tough, I think of them and I think, well, they have each day to struggle, and they're fantastic. And research on rare disorders is not very well supported. The patients have often delays in the diagnosis, also in the care. And I think, they should deserve more help. I myself, when I try to apply for research, sometimes funding agencies prefer to fund disorders that are more common. And so it's a struggle. So what I'm trying to do now is to try to join forces. I think there is only one way to reason with the rare disorders, which is to acquire big numbers. So I'm trying to create collaborations and also create maybe a consortium between scientists, clinicians, and patients' foundations, and gather data from different patients in different countries. But the data should be acquired all in the same way so they could be comparable. And I think that this will be a game changer. In the United States, for example, there was the natural history that actually provided a large number of patients. Now the study is discontinued, but it produced amazing insights. And in Europe, we don't have something similar, but I hope that we'll get there, and possibly that could actually even join forces across the whole globe and be able to collect data. And this is true not only for Rett syndrome, but for all the syndromes. Actually, there are a lot of overlapping features between syndrome.
Well, very good. So how do people keep progress on your work? Because we're close to that of time. What's the best place they can go to find out more?
Yes, so I just started a website, which is under construction, but it will be ready soon. And it's called tropealab.org. I also have in Trinity College my profile, or they can email me. My email is daniela.tropea@tcd.ie. So feel free to contact me and ask for research. And I will have the new website. I had another one, but it was discontinued. So I just started a new one, which should be up and running soon. And so I just want to tell the story of research, because people think that research has eureka moments, right? Moments where you say, I found something.
Right.
But it's not like that. Research is very slow, but it works through discussion between scientists, collaboration. So it's very important to be in a very interactive environment. And also strive with inspiring leaders that lead, but at the same time, they give the freedom to the students and the postdoc to find their own way. And I've been lucky that I had amazing mentors, and I hope I'll be a good mentor myself.
Very good. Well, thank you so much for coming on the podcast. I really appreciate it, Daniela.
Thank you.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.